What if the strangest galaxies in the universe are not cosmic mistakes, but quiet messages written in gravity, dust, and ancient light? Welcome to Slow Space Stories. In this calm journey through deep space, we will drift among galaxies that look almost impossible, a galaxy moving toward us through the Virgo cluster, another leaving star-forming trails like a jellyfish, a distant star factory from the young universe, a dark-eyed spiral turning against itself, and strange rings, tails, and collisions that reveal how the cosmos slowly reshapes itself. Thank you for spending your time here with us. If this kind of peaceful science storytelling helps you relax, wonder, or fall asleep, please like the video, subscribe to Slow Space Stories, and share it with someone who might enjoy a quiet voyage through the universe. Before we begin, feel free to leave a comment telling us what time it is where you are, and where in the world you are listening from. Now, let's begin our slow journey into the most bizarre galaxies scientists have ever discovered. A galaxy is not simply a heap of stars scattered through darkness. It is a vast arrangement held together by gravity, woven from stars, gas, dust, black holes, invisible, dark matter, and the slow memory of everything that has happened to it. At small scales, the universe often appears restless and bright, filled with individual points of light. But galaxies reveal a deeper order. They are the great islands of the cosmos, each one a structure large enough to contain billions of suns, yet delicate enough to be bent by a passing neighbor, stripped by thin cluster gas, or reshaped by an encounter that lasts longer than the whole history of human civilization. Their forms are not random decorations. A spiral arm, a dark dust lane, a glowing ring, or a long tidal tail can be read as evidence of motion, impact, hunger, and survival. In this way, the strangest galaxies are not merely curiosities. They are records, written across enormous distances, of how matter behaves when time is almost without limit. The ordinary image of a galaxy is usually calm and familiar, a flattened spiral, a soft central glow, graceful arms turning through space. The Milky Way belongs to this broad family, though its full shape is difficult to see from within. Yet across the observable universe, this familiar pattern begins to loosen. Some galaxies look like glowing eyes, some resemble wheels, insects, smoke trails, rings, or spilled ink. Some are rushing through clusters so quickly that their own gas is pulled away behind them like a pale cosmic wake. Others are forming stars with such intensity that their light belongs to an earlier, more crowded, more unsettled universe. Still, others appear to rotate against themselves, as if one part remembers a different origin from the rest. Their bizarre shapes matter because galaxies do not change easily. Stars are separated by immense distances, and even during a galactic collision, most individual stars pass one another without touching. What changes is the larger architecture. Gravity pulls on gas and dust. Dark matter halos overlap. Spiral disks stretch into bridges and tails. Clouds of hydrogen compress, cool, and collapse. New stars ignite in places where an older system has been disturbed. The result can be a galaxy that looks wounded, graceful, unfinished, or impossible. The universe does not sculpt these objects quickly. It works through slow pressure, repeated encounters, and the patient accumulation of imbalance. A strange galaxy is often a normal galaxy caught at an unusual moment, or a remnant of events so old that only the structure itself remembers them. The study of these objects begins with light, and light always arrives late. The nearest large galaxies are still seen as they were millions of years ago. More distant galaxies are seen when Earth was very different, or before Earth existed at all. The farthest objects carry images from the young universe. When the first great structures were beginning to assemble, astronomers separate that light into colors, measure how it is shifted, and infer how fast an object is moving, what it is made of, and how its stars are arranged. A galaxy moving away has its light stretched toward redder wavelengths by cosmic expansion. A galaxy moving toward the Milky Way can show a blue shift, with its light slightly compressed. These shifts are not only technical details, they make the universe legible. They reveal that galaxies are not fixed ornaments on a dark surface. They are moving bodies inside a widening cosmos, carried by expansion, drawn by local gravity, and sometimes falling toward one another through the great web of clusters and filaments. At still larger scales, galaxies gather into groups and clusters. These environments are not empty. Between the galaxies lies thin, hot gas, spread so widely that it seems almost absent, yet dense enough to matter when a galaxy moves through it at high speed. A spiral entering a cluster can be stripped of the material it needs to make new stars. Its own gas is pushed back, forming streams that glow in hydrogen and sometimes give birth to stars outside the main disk. Over time, the galaxy may lose the raw material of its future. A structure once rich with star formation can become quieter, redder, and older, not because all its stars have vanished, but because the reservoir from which new stars are born has been taken away. In such places, a galaxy becomes a visible experiment in pressure and motion. The shape of its gas reveals the invisible medium through which it travels. The fate of its stars reveals the price of entering a crowded cosmic city. Other strange galaxies carry the marks of collision. A direct or near-direct impact between galaxies can send a circular wave outward through a disk, making a ring of bright star formation that expands like a ripple on dark water. A slower side encounter can pull a spiral into a long tail of stars, dust, and gas stretching across hundreds of thousands of light years. A merger can feed gas toward a central black hole, brighten a nucleus, and wrap old stars into new arrangements. Some collisions produce disorder that looks violent, but the underlying process is not explosion in the familiar sense. It is gravity, acting everywhere at once, gently and relentlessly changing the paths of stars and clouds. The aftermath can appear dramatic because the scale is so vast. A faint bridge between galaxies may contain more stars than many small galaxies. A curved plume may be the remains of a companion that was gradually torn apart. A ring that seems too perfect may be the last visible clue of an encounter whose intruder has long since moved away or dissolved into the larger system. The strangeness deepens because much of a galaxy is unseen. Stars and gas can be mapped by their light, but the greater mass often belongs to dark matter, which does not shine, absorb, or reflect light in any ordinary way. Its presence is inferred from motion. Stars orbit too quickly to be held by visible matter alone. Gas follows paths that imply a larger gravitational field. In clusters, galaxies move as if embedded in a vast invisible scaffold. When bizarre galaxies are studied carefully, their distorted shapes do more than provide spectacle. They help trace dark matter halos, test how gas responds to pressure, and show how star formation begins or shuts down. A galaxy with a long tail may reveal the pull of a hidden mass distribution. A stripped galaxy may show how ordinary matter separates from the gravitational framework around it. A ring galaxy may preserve the geometry of an ancient encounter, allowing researchers to reconstruct an event that no eye could ever have witnessed directly. There is also a quieter wonder in the fact that galaxies are both enormous and fragile. They can contain hundreds of billions of stars. Yet a thin stream of gas can decide whether their future remains fertile or fades. They can survive collisions that would sound catastrophic in smaller language, because their stars are so widely spaced. Yet their identities may still be transformed beyond recognition. An old elliptical galaxy may carry within its halo the scattered remains of many swallowed dwarfs. A graceful spiral may hide a history of accretion, theft, and repair. A small companion may be slowly stretched until it becomes a barely visible ribbon around its larger neighbor. Nothing in this realm is truly isolated. Every galaxy belongs to an environment, and every environment leaves traces. The bizarre ones make those traces easier to see. They turn faint processes into shapes large enough to recognize. The galaxies that follow are unusual in different ways. Some move toward the Milky Way, while most distant galaxies are carried away by the expansion of space. Some lose their gas in luminous tails. Some blaze with an astonishing rate of starbirth in the early universe. Some wear rings, dark bands, warped disks, or opposing rotations that hint at mergers long past. Together, they form a calm but astonishing procession through cosmic possibility. Their value is not that they break the rules. The deeper truth is more interesting. They reveal the rules at work under extreme conditions. Gravity is still gravity. Gas still cools, compresses, and ignites. Stars still age. Black holes still gather matter when it is driven inward, yet under different pressures, speeds, angles, and histories. These simple principles create forms that seem almost unreal. The universe becomes most understandable not where it is neat, but where it has been disturbed. A bizarre galaxy is therefore not a mistake in the cosmic order. It is an exposed page from the record of that order, showing how immense structures drift, collide, feed, fade, and begin again across the deep. Quiet, dark. In the Virgo cluster, among a dense population of galaxies bound together by mutual gravity, there is a system whose motion seems to run against the wider habit of the expanding universe. Most distant galaxies show light that has been stretched toward the red, not because they are simply flying through space in a straight line, but because space itself has expanded during the long journey of their light. M86 is different when seen from Earth. Its light is shifted toward the blue, a sign that in local cosmic terms it is moving toward the Milky Way rather than away from it. This does not mean it is about to arrive in any human sense, or even in any ordinary historical sense. It lies roughly 52 million light-years from the Sun, beyond a distance so large that the word toward becomes almost abstract. Yet the motion is real. The galaxy is falling through the gravitational landscape of the Virgo cluster, and its approach gives it a quiet strangeness. In a universe where expansion usually makes remote objects retreat, M86 appears as a reminder that gravity has its own local authority. The cluster is a crowded environment by galactic standards, and within it, galaxies do not behave like isolated islands. They pass through a shared medium of hot, thin gas. They tug on one another. They exchange material, and sometimes they leave behind long signs of damage. M86 is usually described as an elliptical or lenticular galaxy, a broad, older system without the graceful blue arms of a classic spiral. At first glance, it can seem calm, almost featureless, a soft glow of old stars. But its still appearance is misleading. It is moving through the cluster at high speed, and that movement has placed it in contact with the faint gas that fills the space between galaxies. This gas is tenuous beyond any earthly comparison, but across galactic scales it behaves like a resisting medium. As M86 plows through it, some of the galaxy's own interstellar material is stripped away. The process is known as ram pressure stripping, a term for the pressure felt by an object moving through a surrounding gas. The effect is not like wind against a tree, because nothing here is solid in that familiar way. It is more like the slow separation of a galaxy from its future reservoir. As gas that might once have formed stars is pushed outward and left behind, the evidence appears in trails of warm, ionized hydrogen, thin, luminous filaments that mark the galaxy's passage through the cluster. Ionized hydrogen is hydrogen whose electron has been removed, and when it glows, it can trace regions where gas has been heated or disturbed. Around M86, these filaments are more than decorative wisps. They are signatures of motion, pressure, and encounter. A galaxy that seems visually smooth is revealed to be shedding material into the space around it. The trail shows that even a massive galaxy can be altered by an environment too thin to imagine directly. In the stillness of a telescope image, a process of removal is underway. M86 is not merely located inside the Virgo cluster. It is being shaped by it. One of the most intriguing parts of its story is its apparent connection with the disturbed spiral galaxy, NGC 4438. That neighboring system has been badly damaged. Its form stretched and unsettled, as though it has survived a severe gravitational encounter. Long streams of gas and dust appear to link the two galaxies, suggesting that in the past they passed close enough for tides to tear at their structures. In galactic terms, tides are not ocean tides, but differential gravity, the uneven pull that stretches one side of an object more strongly than another. If M86 and NGC 4438 did interact, then the encounter may have stripped gas, disturbed stars, and contributed to the strange filaments now observed in the region. The smaller spiral appears almost wounded beside the larger presence of M86. Yet even here, the language of damage must remain careful. Galaxies are not living bodies, and their wounds are not felt. The beauty of the scene comes from matter obeying gravity across distances that dwarf ordinary intuition. A close passage can pull a disk out of shape, remove gas from spiral arms, and send material drifting into intergalactic space. What remains is not a single explosion, but a long aftermath, visible as faint structures that can persist for ages. M86 also carries evidence of an older habit, the absorption of smaller galaxies. Its outer halo contains stellar streams, faint arcs, and trails of stars that are thought to be remnants of smaller systems pulled apart by its gravity. These streams are among the most delicate records in astronomy. A dwarf galaxy may orbit a larger one for a long time, losing stars with each passage, until it becomes no longer recognizable as an independent object. Its stars do not vanish. They are redistributed into the halo of the larger galaxy, forming dim traces of past accretion. M86 appears to have gathered such material repeatedly. Its unusually rich population of globular clusters deepens the impression globular clusters are dense, ancient collections of stars, often containing hundreds of thousands of suns packed into roughly spherical swarms. Observations suggest that M86 may contain more than 3,800 of them, far more than the Milky Way. One possible explanation is that many of these clusters were brought in by smaller galaxies that M86 absorbed over time. In that interpretation, the galaxy becomes less like a single ancient object and more like a composite, an accumulation of many lost systems. Its present form would then contain the memory of destroyed companions, not as dramatic debris only, but as orderly swarms of old stars still orbiting in the dark. The idea is sobering because it changes the meaning of galactic identity. A galaxy has a name, a position, and a visible shape, but it may be assembled from many vanished predecessors. The stars in its halo may have formed elsewhere. Its clusters may be immigrants from small galaxies that no longer exist. Its gas may have been stripped by motion through the cluster or disturbed by encounters with neighbors. M86 therefore stands at the crossing point of several cosmic processes. It is falling inward through a cluster. It is losing material to the medium around it. It may have battered a spiral companion. It has likely consumed smaller galaxies across its past. None of these events needs to be sudden. The total history is a slow rearrangement of ownership. Stars that once belonged to one system become part of another. Gas that might have settled into new stellar generations is carried into filaments. A compact cluster of ancient suns remains intact while the dwarf galaxy that carried it is dissolved. The bizarre nature of M86 is not found in a single impossible shape, but in the layered contradiction between its quiet appearance and its turbulent history. Seen in visible light, it may appear as a smooth, mature galaxy, dominated by older stars and soft contours. Studied more deeply, it becomes active in another sense, not through brilliant star formation, but through motion and stripping, through tidal damage, through the hidden archaeology of its halo. It is one of the galaxies that teaches that stillness in astronomy is often a matter of perspective. A long exposure can make a moving body look serene. A process lasting hundreds of millions of years can appear frozen in one image. A galaxy approaching at hundreds of kilometers per second can seem motionless because the scale of space absorbs all ordinary feelings of speed. The blue shift of M86 is therefore more than a measurement. It is a quiet clue that the local universe is not simply expanding away in all directions like points on a swelling surface. On smaller scales, gravity gathers, redirects, and complicates that motion. Clusters form deep gravitational basins. Galaxies fall through them. Some pass one another. Some merge. Some are stripped and transformed by gas they can barely be said to touch. M86 moves through this basin with a history written in filaments, streams, and clusters. Its approach toward the Milky Way is not a threat, but a sign of the complex circulation inside a nearby cluster. In that circulation, the universe reveals a subtler kind of strangeness. Not every bizarre galaxy must look flamboyant or monstrous. Some are bizarre because their plainness conceals a record of devouring, collision, and slow erosion. M86 is one of these. It comes closer in the dark, carrying the remains of other galaxies in its halo, leaving traces of hydrogen behind it, and moving through Virgo as if the cluster itself were a vast, invisible weather system. Its story prepares the way for another galaxy where stripping is not hidden in faint traces, but drawn across space in long, bright tails. A galaxy whose shape looks less like a quiet island and more like a creature drifting through an unseen sea. ESO 137001 gives the strange process of galactic stripping a more visible form, where M86 hides much of its history in faint filaments and a smooth halo of older stars. This galaxy appears almost theatrical, not because it is performing, but because the physics acting upon it has drawn its condition into space. It lies hundreds of millions of light-years from the Sun, in the direction of a massive galaxy cluster known as Abell 3627. Within that crowded environment, the galaxy is moving at extraordinary speed toward the cluster's central region. It is a spiral galaxy, but it does not look like a calm spiral traveling alone through quiet darkness. Instead, it carries behind it long streams of gas, bright knots, and young stars, forming a shape that has often been compared to a jellyfish drifting through a dark cosmic sea. The comparison is only visual, yet it is useful, because the galaxy seems to have a body and trailing tendrils. The tendrils are not appendages. They are the galaxy's own material, torn away by motion through the thin, hot gas that fills the cluster. The process is called ram pressure stripping, and ESO 137001 is an elegant example. A galaxy cluster is not simply a collection of galaxies gathered in empty space. Between its members lies a vast atmosphere of extremely hot gas, spread thinly across distances so large that its total mass becomes important. A galaxy moving through this medium can feel pressure, even when the gas is far more diffuse than any air found on Earth. The faster the galaxy moves, and the denser the surrounding medium becomes, the more strongly the pressure acts on its own interstellar gas. Stars are not easily stripped by this kind of pressure, because they are compact and bound by gravity in a different way. Dark matter is not pushed aside by ordinary gas pressure at all, but cold and warm gas in the disk of a spiral galaxy is vulnerable. It is the raw material from which future stars would form. When the galaxy plunges through the cluster medium, that gas is pushed backward, peeled from the disk, and drawn into trailing streams. ESO 137001 is being separated from the material that would have allowed it to remain young. Its present shape is therefore not only a spectacle, it is a picture of future loss. The long tails behind the galaxy stretch for immense distances, reaching far beyond the visible disk. They contain hydrogen and other interstellar material, along with regions where new stars have begun to form outside the main body of the galaxy. This is one of the most striking features of the system. Star formation usually belongs inside galaxies, where gas can gather within spiral arms, cool, compress, and collapse. In ESO 137001, the stripped gas does not become silent immediately after removal. Parts of it remain dense enough, or are compressed enough by the surrounding environment, to ignite new stars in the wake. The galaxy is leaving behind not only debris, but a trail of birth. Blue young stars shine within material that has been removed from the place where it once belonged. The result is deeply paradoxical. The same process that weakens the galaxy's long-term ability to form stars also triggers star formation in the gas that has been torn away. Destruction and creation occupy the same tale. The main disk of ESO 137001 still contains stars, but the loss of gas changes its destiny. A spiral galaxy depends on gas to maintain its luminous youth. Without a continuing supply, its star formation fades. Massive blue stars die quickly, leaving behind longer-lived yellow and red stars. Spiral arms become less sharply marked by bright newborn clusters. Over time, a galaxy that once had active star-forming regions can become quieter and more aged in appearance. In ESO 137001, the stripping is severe enough that much of its star-forming material is being pulled away into the surrounding cluster. The galaxy is not being destroyed in an instant. Its stars will continue to orbit. Its dark matter halo will remain largely unaffected by the pressure that removes ordinary gas. But its future is being edited. The reservoir from which new generations of stars would have emerged is being carried away, and the galaxy is moving toward a quieter state shaped by environmental exhaustion. This makes the object valuable to astronomers because it reveals several layers of cluster physics at once. The tails trace the motion of the galaxy through the intracluster medium, the hot gas between galaxies. Their shape offers clues about the density, turbulence, and pressure of that medium. The locations of star-forming knots show how stripped gas behaves after it leaves the disk. The separation between stars, gas, and dark matter helps clarify how different kinds of matter respond to the same journey. Ordinary gas can be dragged away. Stars, being much denser and less directly affected by pressure, remain more closely tied to the galaxy's gravity. Dark matter, invisible except through its gravitational influence, does not interact with the surrounding gas in the ordinary way. A single galaxy moving through a cluster therefore becomes a natural laboratory. Its motion provides the experiment. Its tails preserve the result. The beauty of ESO 137001 comes partly from the way scale transforms violence into calm. The galaxy is racing at roughly 2,000 kilometers per second, a speed that would be unimaginable for any ordinary object. Yet in telescope images, it seems suspended, almost gentle. The wake trails behind it in soft blue and pink structures. The stripping has probably unfolded across tens or hundreds of millions of years. So the event cannot be understood as a sudden tearing motion. It is a long passage through resistance. The galaxy continues forward while its gas falls behind, and the surrounding cluster medium shapes the stripped material into flowing filaments. This is cosmic weather at a scale beyond instinct. There is no wind in the everyday sense, Yet the result resembles a body moving through an unseen current. The galaxy has become a weather vane for the cluster itself, pointing through its own loss toward the invisible gas around it. It also shows that galaxies are transformed not only by direct collisions with other galaxies, but by the environments they enter. A spiral may pass through a cluster without smashing into another spiral, and still its life can be altered profoundly. In field regions, far from dense clusters, a galaxy may keep its gas and continue forming stars over long spans of time. In a cluster, the same kind of galaxy can be stripped, quenched, and gradually changed. Quenching means the slowing or stopping of star formation, and in clusters it can occur when gas is removed, heated, or prevented from cooling. ESO 137001 appears at a dramatic stage of that transformation. It has not yet become a quiet remnant. It still carries fresh stars, active gas, and a recognizable disk. But the direction of change is visible. The tails behind it are like a ledger of what has been taken. The young stars within those tails are brief lights in material that no longer belongs securely to the galaxy. There is a faint sadness in this. Though the science itself remains steady, the galaxy is not suffering. It is following the combined demands of gravity and motion. Yet its form suggests a loss of continuity. A spiral galaxy is often imagined as a system that renews itself, slowly turning gas into stars while preserving its pattern over immense timescales. Here, the pattern is interrupted by entry into a harsher environment. The galaxy's blue stars reveal recent creation, but the stripped gas reveals that creation may not continue in the same way. Its most beautiful feature is also a sign of depletion. The tails are luminous because material is still active, still forming stars, still responding to pressure and compression. But they also announce that the galaxy is being deprived. Over time, the wake will disperse, the young stars will age, and the main disk will have less fuel for new generations. To study ESO 137001 is to watch a galaxy at the boundary between its past and its likely future. It carries the familiar architecture of a spiral into the crowded depths of a cluster, and the cluster answers by removing the gas that made that architecture luminous. Behind it, star-forming streams draw delicate lines through intergalactic space. Ahead of it lies the dense central region of the cluster, where the pressure may become still stronger. The galaxy's story is not only about what it looks like, but about what it is losing as it moves. Its bizarre form turns an invisible process into a visible structure. It shows that even the emptiness between galaxies has force, and that the spaces inside clusters are not passive. They can reach into a galaxy without touching its stars directly, remove its gas, and alter the rhythm of its future. In that sense, ESO 137001 is one of the clearest reminders that a galaxy is never only itself. It is also the place through which it travels, the medium it crosses, and the pressure it cannot escape. The baby boom galaxy carries the story of strangeness away from nearby clusters and into the early universe, where distance becomes a kind of time machine. Its light has traveled for more than 12 billion years before reaching telescopes near Earth. So the galaxy is seen not as it is now, but as it was when the cosmos was still young. At that time, the universe had not yet settled into its later, more familiar pattern of mature spirals, quiet ellipticals, and clusters filled with old red stars. Matter was still gathering into large structures. Gas was more abundant. Galaxies were colliding and assembling more frequently, and the first long chapters of cosmic architecture were still being written. In this setting, the baby boom galaxy stands out because of the rate at which it appears to create stars. It is extreme. Observations suggest that thousands of new stars may form there in a single year, far beyond the Milky Way. It represents a period when star formation could run with an intensity difficult to sustain in the calmer universe nearby. A star is born when gas, mostly hydrogen, becomes dense and cold enough for gravity to pull it inward. The cloud contracts, fragments, and forms a central object that grows hotter as it gathers mass. When the core becomes hot and dense enough, nuclear fusion begins, and a new star enters the long record of light. In an ordinary star-forming galaxy, this process happens inside molecular clouds, spread through spiral arms or central regions. It is not simple or uniform. Gas must cool. Turbulence must be overcome in some places and useful in others. Magnetic fields, pressure, gravity, and feedback from young stars all shape the outcome. In the baby boom galaxy, these ingredients seem to be arranged in a way that allows star formation on a vast scale. The galaxy is turning gas into stars with exceptional speed, as though a great reservoir of material has been compressed and set alight across many regions at once. The result is known as a starburst, an episode in which a galaxy forms stars far faster than usual. Many starburst galaxies are triggered by mergers or close encounters, because gravitational disturbance can drive gas inward, compress clouds, and ignite widespread formation. For the baby boom galaxy, the deeper mystery is not only that star formation is intense, but that it is observed so early in cosmic history. Its light comes from a time when the universe was only a small fraction of its present age. Under simple expectations, galaxies in that era might still be building up gradually, not already producing stars at such a tremendous rate. Yet the universe often resists simple schedules. Some systems grow quickly. Some gather gas efficiently. Some may sit at the meeting points of large cosmic filaments, where streams of cold material feed them from the surrounding web. Some may experience mergers that concentrate gas and trigger bursts of formation. The baby boom galaxy may be a sign that large, luminous galaxies could assemble rapidly under the right early conditions. It suggests that the young universe was not merely a dim prelude to later grandeur, but already capable of enormous productivity. If thousands of stars form each year, then the galaxy is changing visibly in a cosmic sense. Even though no human lifetime could follow the full transformation directly, every brief interval adds new suns. Some are likely small and long-lived, destined to burn quietly for immense spans of time. Others are massive, blue, and short-lived, spending their fuel quickly before ending in brilliant supernova explosions. These massive stars are especially important because they do not only shine, they reshape their surroundings. Their radiation heats and ionizes gas. Their winds push against nearby clouds. Their deaths scatter heavier elements, enriching the galaxy with carbon, oxygen, iron, and other atoms made in stellar interiors or explosive endings. In a starburst galaxy, this feedback can become powerful enough to regulate or even disrupt further star formation. A galaxy that burns too intensely may begin to drive away the gas it needs. Creation contains the seed of its own slowing. The baby boom galaxy therefore sits inside a delicate balance between abundance and exhaustion. On one side, it must have access to a large supply of star-forming material. On the other, the stars it creates quickly begin to alter that material. Radiation, stellar winds, and supernova shocks can carve cavities, steer turbulence, and launch gas outward. If a central black hole is also growing, the energy released by infalling matter may add another form of feedback. The galaxy's brilliance can become a force acting against its own continuation. This is one reason extreme star formation cannot usually continue indefinitely. A starburst may be spectacular, but it is also consuming. It turns a reservoir into a population of stars, and in doing so, changes the reservoir itself. What appears as abundance from a distance may be a short, intense phase in a longer life that later becomes quieter. Because the baby boom galaxy is so far away, much of what is known about it depends on light beyond the range of ordinary sight. Dust plays a central role in star-forming galaxies. Young stars are often born inside dusty clouds that absorb visible and ultraviolet light. That absorbed energy is then re-emitted at longer infrared wavelengths. Telescopes designed to detect infrared radiation can reveal star formation hidden behind dust, making it possible to estimate how rapidly a distant galaxy is producing stars. In the early universe, this task becomes more complex because cosmic expansion stretches light toward longer wavelengths before it arrives. The galaxy's radiation has been redshifted, carrying information not only about its internal activity, but also about the expansion of space during the journey. To study such a galaxy is therefore to read a message translated by distance, dust, and time. It tells of dense gas, young stars, heating, obscuration, and an era when galaxies could grow at astonishing speed. The baby boom galaxy also belongs to a broader question in cosmology. How did the universe move from smooth beginnings to the complex structure seen today? Tiny differences in density allowed gravity to gather gas and dark matter into larger concentrations. The cradles of galaxies. Over time, small systems merged into larger ones. Gas cooled into disks. Stars formed, and heavy elements accumulated. The baby boom galaxy appears as a bright landmark in that process, showing that galaxy formation was uneven, clustered, and sometimes explosive in its productivity. Some regions of the young cosmos may have raced ahead, while other areas remained comparatively faint. The universe was young, but not empty of complexity. There is a calm astonishment in considering that the light from this galaxy began its journey before the Sun, Earth, and the Milky Way's present details had fully taken shape. The stars seen forming there may have lived and died billions of years before the solar system existed. Their explosions may have seeded their surroundings with heavier elements long ago. The galaxy itself may no longer resemble the object observed in ancient light. It may have merged with others, exhausted much of its gas, grown a central black hole, or become part of a larger structure. Astronomers do not see its current face. They see a chapter preserved by distance. This is one of the strange gifts of astronomy. The sky does not present a single universal now. It presents many layers of time. Nearby galaxies show relatively recent histories. Distant galaxies reveal earlier epochs. A system like the baby boom galaxy is both an object and an archive, not because it stores written memory, but because its light left during a formative period of cosmic history. Its bizarre nature lies less in its shape than in its intensity. It is a firestorm of stellar birth observed at an age when such activity helps test the models of how galaxies grow. It asks how gas was gathered so efficiently, how dust formed so early, how star formation proceeded so rapidly, and how such a burst affected the galaxy's later fate. The answers are not found in one feature alone, but in the combined evidence of infrared light, redshift, mass, dust, and comparison with other early galaxies. The baby boom galaxy widens the parade of bizarre systems beyond distorted forms and stripped tails. It shows that a galaxy can be strange because of what it is doing, not only because of how it looks. In M86, strangeness appears in motion toward the Milky Way and in the scars of encounters. In ISO 137001, it appears in gas, stripped into luminous wakes. Here, it appears in abundance pushed to an extreme. In star birth, accelerated until the galaxy becomes a furnace of beginnings. The image is not violent in the ordinary sense. It is immense and generative, a distant region where gravity, gas, and time combine to produce light at a rate almost beyond comparison. Yet even this abundance is part of a cycle. Stars form, shine, change their surroundings, enrich the gas, and eventually die. The galaxy that seems to blaze with newness is already preparing the materials and consequences of its future. Across the early dark, the baby boom galaxy reminds astronomy that the universe did not wait patiently to become complex. In some places, it rushed into brilliance, building stellar populations with startling speed, leaving distant light to show that cosmic youth could be as strange and powerful as cosmic old age. The Sombrero Galaxy changes the rhythm of the procession. After the distant blaze of the baby boom galaxy, it brings the gaze back toward a nearer and quieter universe, where strangeness does not announce itself through overwhelming starbirth, but through form. It lies around 30 million light-years from the Sun, close enough by extragalactic standards to be seen with modest instruments under good conditions, and yet far enough away that its light still began the journey long before any human eye could notice it. Its familiar nickname comes from its shape. A bright central bulge rises above a broad, dark band of dust, giving the impression of a wide brim around a luminous crown. In visible light, it is one of the most recognizable galaxies in the sky, but the apparent simplicity of the image is misleading. The sombrero is not merely a pretty silhouette. It is a system whose structure seems to contain more than one galactic identity, as though several histories have been folded into a single calm outline. The dark ring is the feature that first commands attention. It is made of dust and gas, including cold hydrogen, arranged in a broad disk around the galaxy. Dust in astronomy is not household dust, but tiny grains of carbon, silicon, oxygen-bearing compounds, and other heavier materials created in earlier generations of stars. These grains absorb and scatter light, so when they gather into a dense lane, they can carve a dark line across a bright background. In the Sombrero Galaxy, the dust band is so strong that it seems almost like an edge, a boundary drawn between the shining bulge and the outer darkness. Yet it is not only an obstruction, it is also a region of activity. Gas in and near the ring can cool and gather into clouds, and within those clouds, new stars can form. Young stars are not evenly spread through the whole galaxy. Much of the visible birth belongs to this dusty, rotating structure, where the raw ingredients for new suns remain available. Around it, the older stellar body tells another story. Observations at infrared wavelengths, which can pass through dust more easily than visible light, reveal that many of the Sombrero Galaxy's stars are arranged in a way more typical of an elliptical galaxy than a classic spiral. Elliptical galaxies are generally dominated by older stars, moving on more varied orbits, forming smooth, rounded shapes rather than thin disks with bright arms. The sombrero has such an old, massive, central component, filled largely with yellow and red stars that have lived quietly for long spans of time. At the same time, it also contains a disk and spiral-like material embedded within or wrapped around that older body. This combination makes it hard to place neatly into a single familiar category. It looks like a spiral seen almost edge-on, yet much of its stellar mass behaves like part of an elliptical system. Its bizarre quality comes from this overlap, a galaxy wearing the outline of one family while carrying the weight and age of another. One possible explanation is an ancient merger or long sequence of accretion events. When galaxies merge, their gas and stars do not simply mix like liquid. Stars pass through one another because the distances between them are immense, but their orbits can be changed by the shifting gravitational field. Gas, unlike stars, can collide, shock, cool, and settle into disks or rings. If a spiral galaxy and a more elliptical system were brought together, or if a large early galaxy acquired gas and smaller companions over time, the result could be a structure in which an old spheroidal body coexists with a younger dusty disk. The sombrero may preserve such a layered origin. Its present serenity would then be the late stage of a more unsettled past. The collision or assembly that shaped it no longer looks like chaos. It has relaxed into symmetry, leaving behind a bright bulge, a dust ring, and hidden spiral traces as the remaining evidence of transformation. The galaxy's central region deepens the mystery. At its heart lies a supermassive black hole, an object whose mass is measured in hundreds of millions to more than 1 billion suns. A black hole itself gives off no light from within its event horizon. The boundary beyond which escape is impossible, but matter falling toward it can become extremely hot before crossing that limit. Gas in an accretion disk may radiate strongly as friction. Compression and gravity convert orbital energy into heat. The Sombrero Galaxy produces powerful radiation from its center, including X-ray emission, suggesting that its central black hole is not simply a silent mass buried in darkness. It is modest compared with the most brilliant active galactic nuclei, but it remains a sign that material has been drawn inward. The same galaxy that appears so neatly composed from afar contains at its core one of the most extreme gravitational objects in nature. This contrast between elegance and intensity is part of its fascination. The ring, the bulge, and the black hole all belong to the same system, but they speak in different timescales. The dust ring traces ongoing or recent star formation and the motion of gas. The old bulge carries a population that may have formed much earlier, perhaps during the galaxy's main assembly. The black hole reflects the long accumulation of mass at the center, growing through gas inflow and perhaps through mergers with other black holes as smaller galaxies were absorbed. A galaxy is often described as one object, but in truth it is many histories synchronized only by gravity. In the Sombrero, those histories remain unusually visible. The old stars glow steadily. The dust ring blocks and re-radiates light. The central black hole exerts a hidden authority. Each component reveals a different layer of evolution, and none completely explains the others by itself. The Sombrero's richness also appears in its surrounding population of globular clusters. These compact swarms of ancient stars orbit through the galaxy's halo, and their large number suggests a deep and active assembly history. Globular clusters often survive events that disrupt the smaller galaxies that carry them. If the Sombrero absorbed companions over time, some clusters may have been added from those lost systems, becoming part of its extended family of old stellar relics. Their presence strengthens the impression that the galaxy is not an untouched island, but a collector of past structures. Around its polished shape may lie the evidence of many smaller histories, now dimmed into the halo. The smoothness of the Sombrero is therefore not innocence. It may be the smoothness that follows a long period of gravitational sorting. Disturbed material settles. Stars find stable paths. Gas forms a disk. The visible remnant becomes beautiful because time has softened the violence of its making. There are still details not fully resolved. Some observations have revealed unusual high-frequency radiation from within the galaxy, and the exact origin of every energetic source is not always simple to identify. Some may be related to star-forming regions, compact stellar remnants, dust heated by radiation, or activity near the central black hole. In a galaxy with such layered structure, light from different processes overlaps. Dust hides some regions while revealing itself at longer wavelengths. Old stars dominate one view, young stars another, hot gas another. The Sombrero must therefore be studied not as a single picture, but as a set of portraits made in different kinds of light. Visible images show the dramatic dust lane. Infrared observations uncover the older and hidden stellar body. X-ray observations expose energetic processes near the center and compact sources scattered through the system. Each wavelength removes one veil and adds another. The final galaxy is reconstructed from all of them, never seen completely by any single form of light. What makes the Sombrero especially fitting among bizarre galaxies is that it appears orderly at first. Its strangeness is not the strangeness of a torn tail or a lopsided wound. It is the strangeness of a structure that refuses to belong cleanly to one category. It asks whether classification can sometimes hide the deeper story. A galaxy may be called spiral, elliptical, or lenticular, but its real history may include collisions. accretion, gas, settling, black hole growth, and the survival of ancient clusters. The sombrero rests at the border of these descriptions. It has the visual drama of an edge-on disk, the mass and old light of a spheroid, the dusty material of continued star formation, and the central gravity of a giant black hole. It is both composed and complicated, simple in outline and layered in origin. In this way, it serves as a bridge between the visibly disturbed galaxies and the more inwardly peculiar ones. It shows that a galaxy can keep its secrets inside a beautiful shape. The dark ring that gives it a name may be only the most obvious sign of a deeper merger of identities. Beneath the brim, the galaxy preserves old stars, concealed structures, energetic radiation, and a central darkness heavy enough to shape the motion around it. Its beauty is not separate from its science. The same features that make it recognizable also make it instructive. The Sombrero Galaxy is a reminder that even the most graceful cosmic forms may be assembled from events of pressure, impact, and absorption, later quieted by time until the evidence rests in a luminous bulge and a ring of dust suspended against the deep background of space. The Black Eye Galaxy, known as M64, has a name that seems almost too direct for an object made of stars. Its most recognizable feature is a broad, dark band of dust crossing part of its bright central region, like a shadow pressed against a luminous face. In ordinary visible light, this dust lane gives the galaxy its familiar nickname, because it appears to bruise or cover one side of the core. Yet the darkness is not empty. It is made of fine grains and gas lying between the galaxy's stars and the observer, absorbing and scattering light from behind it. The effect is visual and dramatic, but it is only the first layer of the galaxy's strangeness. M64 is not merely a spiral galaxy with an unusual dust lane. Beneath that dark mark, its inner and outer regions do something far more surprising. They rotate in opposite directions, as if the galaxy contains two memories of motion held in the same body. This counter-rotation makes the Black Eye Galaxy one of the clearest examples of how a galaxy can preserve evidence of an ancient disturbance, not only in its shape, but in its movement. It lies roughly 17 million light-years away, close enough for astronomers to examine its structure in detail, and it is smaller than the largest spirals, with a bright central region surrounded by a disk of stars and gas. In many respects, it could appear familiar. It has a luminous nucleus, a dusty inner zone, and a stellar disk arranged around a common center. But when the motion of its gas is measured, the familiar picture breaks. The stars in the main body and the gas in the inner region turn one way, while a larger outer disk of gas turns the other. This is not a trivial difference. Like a swirl or local turbulence, it is a large-scale reversal, a sign that part of the galaxy's material was probably acquired from outside rather than formed with the original system. A galaxy born from one rotating cloud of gas should normally carry a shared sense of spin. Locale complications can arise, and bars or spiral waves can redirect motion, but a broad counter-rotating component points toward a more dramatic origin. The likely explanation is a merger or accretion event in the distant past. M64 may have absorbed a smaller gas-rich galaxy whose rotation happened to be opposite to its own. As the smaller system was torn apart, its stars and gas became mixed into the larger galaxy. But the incoming gas kept much of its original angular momentum, the quantity that describes rotational motion. Over time, that gas settled into an outer disk rotating against the inner galaxy. The encounter did not need to destroy M64. It only needed to add material with the wrong spin. The result is a galaxy that looks unified from afar, but is dynamically divided. The word divided is important, because the counter-rotation is not merely an old scar frozen in place. It continues to affect the galaxy's behavior. Where gas moving in opposite directions meets or interacts, collisions and shocks can occur. Gas clouds do not pass through one another as easily as stars do. They can compress, heat, lose energy, and change their orbits. In M64, the boundary between the inner and outer gas systems becomes a region where disturbance can encourage star formation. Clouds, compressed by their unusual motion, may collapse into new stars, leaving bright young populations within a galaxy whose structure was shaped by an older collision. Once again, the strange pattern carries both destruction and renewal. A smaller galaxy may have been pulled apart, but some of its material became fuel for later birth. The dark dust lane across the central region gains deeper meaning in this context. It is not just a shadow producing a memorable shape. It is part of a disturbed inner environment where gas and dust have been gathered, compressed, and arranged by past gravitational events. Dust lanes in spirals often trace dense material associated with star formation. But in the Black Eye Galaxy, the lane sits within a system whose motion is unusually complex. The bright nucleus behind it suggests concentration and activity, while the obscuring band shows that cold material still lies in the central regions. Because dust blocks visible light, it also limits simple estimates of the galaxy's stellar content. Some stars are hidden, some regions are dimmed, and the true arrangement must be reconstructed with observations in other wavelengths. Infrared light can penetrate dust more effectively, while radio observations can map hydrogen gas and reveal motion that visible images cannot show. Through these different forms of light, the galaxy becomes less like a face with a dark mark and more like a machine of opposing rotations. Counter-rotation also changes the emotional quality of the object. Many peculiar galaxies look strange because they have been stretched outward, broken into tails, or wrapped into rings. M64 keeps its disturbance closer to home. Its body remains compact and recognizable. The violation is internal. One part of the galaxy turns against another, not in conflict with intention, but through inherited motion from different origins. This gives it a quiet tension. The galaxy does not appear chaotic in the way of two spirals actively colliding. It appears settled enough to have a clear disk and a bright center. Yet its gas remembers an event that did not fully dissolve into uniformity. Time has smoothed the image, but not erased the angular momentum. In this sense, M64 is a record of how galaxies digest smaller companions. The visible debris of a merger may fade. Tidal tails may disperse. Stars from a swallowed system may blend into the halo. But motion can remain as evidence long after the shapes become hard to recognize. The Black Eye Galaxy teaches that galactic archaeology is not limited to looking for streams and shells. It also involves listening, through measurement, to how material moves. Rotation curves, gas velocities, and spectral shifts reveal histories that ordinary images might miss. When astronomers measure light from different regions of a galaxy, they can determine whether material is moving toward or away from Earth. By mapping those shifts across the disk, the direction and speed of rotation emerge. In M64, that map reveals the reversal. The galaxy's secret is not hidden because it is small. It is hidden because it is kinetic. Its deepest oddity is a pattern of motion. There is a special delicacy in the conditions that may have produced it. For counter-rotation to be so clear, the incoming smaller galaxy likely needed a particular orientation, enough gas to leave a lasting component, and a merger path that did not simply scramble everything beyond recognition. If the encounter had been too violent, the disk might have been more completely disrupted. If the incoming material had been too little, the reversal might have faded into a minor irregularity. If the angle had been different, the gas might have settled into a warped disk rather than a counter-rotating one. M64, therefore, suggests not only a collision, but a collision with a fortunate geometry, at least from the standpoint of later observation. The universe produced an arrangement rare enough to be instructive and close enough to be studied with care. This is why the Black Eye Galaxy is more than a nickname attached to a striking photograph. Its dark band makes it recognizable, but its reversed motion makes it profound. It demonstrates that a galaxy's present appearance can be a compromise between older structure and acquired material. The original system may have kept its central body, while the captured gas formed an opposing outer disk. Star formation may then have emerged where those components interacted. The galaxy became not a simple survivor, but a hybrid of motions. Its black eye is the visible emblem of a deeper merger, a surface mark over an interior that turns in two directions at once, compared with the Sombrero Galaxy, which hides a complex identity inside an elegant shape. M64 reveals a different kind of hidden complexity. The sombrero's layered nature lies in the coexistence of an old spheroid, dusty disk, and massive black hole. The black eye's layered nature lies in rotation itself. Both show that beauty in galaxies often follows disturbance, and that classification by shape can miss the most important history. A spiral can contain an opposing flow. A dark dust lane can mark the edge of a past merger. A bright center can shine behind material brought inward by events that happened long before the current image. In the slow time of galaxies, even contradiction can become stable for a while. M64 holds that contradiction with unusual clarity. Its inner region and outer gas do not share one simple origin, yet they remain bound around the same gravitational center. The galaxy is not falling apart. It is carrying its divided past forward, turning in the dark with two inherited directions. In that motion, the Black Eye Galaxy becomes a calm lesson in cosmic memory. Some histories are written in tails and rings. Some are written in young blue stars. Some are written in a shadow across a bright core. And some, like this one, are written in the quiet reversal of a galaxy's spin, where the aftermath of an ancient merger continues to circle around the light it helped reshape. Hoag's object seems at first to belong less to astronomy than to geometry. Against the deep background of space, it presents a calm yellow core surrounded by a nearly perfect ring of blue stars, with a wide, dark gap between them. It does not have the obvious arms of a spiral galaxy, nor the smooth, continuous glow of an ordinary elliptical. It looks almost designed, as though one galaxy had been placed inside another without touching it. Yet the appearance is natural, and that is what makes it so unsettling in the quietest way. The universe has many methods for creating rings: arch, shells, and tails. But Hoag's object resists simple explanation. Its symmetry is too clean to dismiss. In many ring galaxies, the origin is a collision. A smaller galaxy passes through or near the disk of a larger one, sending a wave of compression outward through the gas. As that wave travels, it triggers star formation in a circular front, producing a bright blue ring around an older center. The Cartwheel Galaxy, which follows later in this procession, is a classic example of that kind of impact. Hoag's object, however, does not reveal the same obvious signs. It has no clear intruder nearby that can be confidently blamed. It does not show a messy wake, a long tail, or a strongly disturbed disk that would make the event easy to reconstruct. The central body is smooth and yellowish, dominated by older stars, while the surrounding ring glows with younger, bluier stars. Between them lies a gap that appears almost empty by comparison. The result is not a ripple frozen in chaos, but a luminous arrangement so balanced that it feels like a question left in the sky. The central core of Hoag's object resembles an elliptical galaxy or a compact spheroid, a rounded concentration of older stars moving in many directions rather than in a flat, orderly disk. Its color suggests a population that is no longer rich in massive young blue stars. These older stars shine with steadier, warmer light, giving the center a quiet maturity. The ring, by contrast, is blue because it contains younger, hotter stars that burn brightly and live comparatively short lives. Their presence implies that gas exists in the ring and has recently formed new stars. A galaxy with an old center and a young outer ring is already telling a divided story. One part speaks of age and settled motion. The other speaks of recent formation and cold gas. The gap between them sharpens the mystery because it separates these histories instead of blending them smoothly. If the ring were merely the outer part of a spiral disk, traces of arms or connecting material might be expected. In Hoag's object, the separation appears unusually clear. Several ideas have been proposed to explain this arrangement, and none removes the mystery completely. One possibility is that Hoag's object formed from a past collision or close gravitational encounter whose visible traces have mostly faded. If an intruding galaxy passed through long ago, it might have launched an expanding ring of star formation, leaving the central core behind. But the regularity of the object and the lack of an obvious culprit make this explanation incomplete. Another possibility is that the ring formed through accretion, as gas from outside the central galaxy settled into orbit and began forming stars. In that case, the blue ring might be material gathered from a smaller companion or from the surrounding environment, arranged into a rotating structure around the older core. A third possibility involves a more subtle internal process, where instabilities or resonances shaped gas into a ring. Resonance, in this sense, means a pattern in which orbital motions reinforce certain regions, allowing gas to collect there. Yet Hoag's object lacks the common bar structure often associated with ring resonances in disk galaxies. Each explanation carries part of the answer and leaves part of the silence intact. The object becomes especially fascinating because it is not alone in concept, yet remains rare in clarity. Ring galaxies exist across the universe, but most show evidence of disturbance, asymmetry, or an ongoing interaction. Hoag's object appears almost pristine. Its outer ring is not perfectly uniform, but it is close enough to appear serene. Its center sits within it like an island in a dark lake. Even more strangely, another ring galaxy can be seen far beyond it in the background, visible through the open space between the core and the ring. This distant alignment is accidental, but it deepens the sense that the image is layered with improbability. One ring galaxy frames another, separated by vast distances, with no physical connection between them. To understand Hoag's object, astronomers must measure not only its appearance, but its motion. If the ring rotates in a stable way around the central body, that motion can reveal whether the two components are gravitationally bound as one system and how mass is distributed between them. The unseen dark matter halo may play a major role in holding the structure together. Dark matter does not glow, but its gravity shapes the orbits of stars and gas. A ring separated from a central core may be especially sensitive to the underlying gravitational field. If the halo is extended and balanced, it could allow the ring to remain coherent over long periods. If the structure came from an ancient encounter, the dark matter distribution would influence how the visible material settled afterward. In this way, Hoag's object is not only a visual oddity, it is a test of how visible matter can arrange itself inside an invisible gravitational scaffold. The contrast between old and young stars also raises questions about the supply of gas. The central core appears to have little active star formation, while the ring clearly contains the conditions needed to produce new stars. How did the gas arrive in the ring without filling the gap? Did it once belong to a larger disk that was stripped or rearranged? Was it captured from another galaxy and deposited at a distance from the center? Did a collision remove or heat the material between the two zones, leaving the ring as the only place where cold gas survived? These questions matter because star formation depends on environment. Gas must be cool and dense enough to collapse, but it must also be placed where gravity and pressure allow clouds to gather. Hoag's object seems to have created a favorable zone far from its core, while the region between remains comparatively empty. There is a restraint in its beauty. Some galaxies look bizarre because they seem torn open. Hoag's object looks bizarre because it seems too undisturbed. Its puzzle is not excess, but precision. The central glow and the outer ring do not appear to be colliding now. The system is quiet enough that whatever formed it may have happened far in the past, giving time for the most chaotic evidence to fade. Yet the blue ring cannot be ancient in the same way as the core, because blue stars do not last for the longest cosmic spans. This means the ring either formed recently, continued forming stars over a long period, or has been refreshed by a lasting gas supply. The galaxy is therefore both settled and active, old and young, simple and unresolved. Its calm shape conceals competing timescales. Hoag's object also challenges the habit of treating galaxies as clearly classified things. It is not a normal elliptical because of the separated star-forming ring. It is not a normal spiral because the ring lacks ordinary arms attached to the center. It is not a typical collisional ring because the evidence for a recent impact is subtle or missing. It occupies a narrow and strange category, useful precisely because it does not fit. Such objects help astronomy by exposing the limits of familiar labels. Classification is a beginning, not an ending. A galaxy's shape may suggest a history, but the history must be tested through color, motion, gas content, environment, and comparison with simulations. Hoag's object remains important because its form is so clean that every explanation must meet a high standard. The outer ring must be explained. The old core must be explained. The gap must be explained. Their coexistence must be explained without inventing evidence that is not there. In the quiet procession of bizarre galaxies, Hoag's object becomes a pause of almost mathematical wonder. After the Black Eye Galaxy, where opposite rotations betray a swallowed companion, this object presents another kind of galactic memory, one written not in conflict of spin, but in separation. Its core and ring seem to hold apart while remaining connected by gravity. It is a system built around absence as much as light. The dark gap is not merely empty space in the image, it is part of the mystery. A region where the expected bridge between old center and young ring is missing or faint. Around that absence, stars continue to shine. The yellow core keeps the patience of an older galaxy. The blue ring keeps forming new light at the edge. Together they form one of the most peculiar and beautiful structures known, not because it breaks the laws of physics, but because it shows how many different pathways those laws may allow. Hoag's object is a reminder that the universe can produce strangeness not only through violence, but through balance, through clean separation, and through a symmetry that remains unexplained enough to feel almost dreamlike. The Cartwheel Galaxy seems to show a single moment stretched across hundreds of millions of years. It is not a quiet disk with spiral arms turning around a familiar center, nor a smooth elliptical softened by age. It appears instead as a vast ring, bright along its rim, crossed by faint spokes of material, with a disturbed center set inside the wheel. The shape is so unusual that its name feels almost inevitable. Yet the cartwheel is not a designed object, and it is not a frozen ornament. It is the aftermath of impact. Long ago, another galaxy likely passed through or very near the middle of a larger disk galaxy. The stars themselves did not collide in the ordinary sense, because stars are tiny compared with the distances between them. But gravity changed the arrangement of the whole system. Like a stone dropped into still water, the passage sent a wave through the disk, compressing gas as it moved outward. Where the wave passed, gas clouds became dense enough to form new stars. The glowing outer ring is therefore not only a shape, it is a moving front of star birth, a circular disturbance still expanding through the remains of an older galaxy. The collision that made the cartwheel was not an explosion from the center. It was a gravitational event, a deep rearrangement caused by a passing intruder. Before the encounter, the larger galaxy may have looked more like a normal spiral, with gas, dust, stars, and a central region bound inside a rotating disk. Then a smaller galaxy plunged through. The intruder's gravity pulled on the disk from different directions as it passed. disturbing stellar orbits and pushing gas into a wave. Because gas can collide with gas, unlike stars that mostly pass through empty space. It responded strongly. It compressed, shocked, cooled in some places, and gathered into the outer ring. Stars that were already present were also redirected, but they did not light the rim in the same way. The outer ring is blue and bright because it contains massive young stars formed in the compressed gas. These stars are short-lived on cosmic scales. So, their presence reveals that the ring is not merely an ancient leftover. It is an active region where the aftermath of the collision continues to generate light. Inside the ring, the galaxy's structure appears broken and open. Faint radial features stretch between the center and the rim, creating the impression of spokes. These are not solid struts, but streams and patterns of stars, gas, and dust shaped by gravity after the encounter. Some may trace material left behind as the density wave moved outward. Some may mark the paths of stars whose orbits were disturbed and elongated. The central region contains older stars and ongoing activity, but it no longer commands the appearance of the whole galaxy as a calm spiral bulge might. The rim has become the dominant feature, as though the galaxy's active life has migrated outward into a luminous boundary. The contrast between center and ring gives the cartwheel its peculiar stillness. It looks like a wheel at rest, but its meaning is motion. The outer edge is not simply sitting there. It represents a wave that has traveled across a galactic disk, carrying compression and star formation with it. The scale of the ring is immense, extending across a diameter larger than that of the Milky Way. A disturbance that began with the passage of one galaxy through another has grown into an architecture spanning more than 100,000 light-years. It may take hundreds of millions of years to cross the disk. Yet during that time, it reshapes the visible identity of the galaxy completely. If seen at a different epoch, the cartwheel might have looked less strange. Before the impact, it may have been a spiral, far in the future. The ring may fade. The disturbed stars may settle into new orbits, and the system may become harder to recognize as a clean wheel. The present view is therefore a rare phase, a temporary geometry preserved by the fact that light from the galaxy reaches Earth during this chapter of its evolution. The cartwheel also shows how collisions can trigger creation without requiring direct contact between stars. In ordinary language, a collision suggests destruction through impact, but in galaxies, the word means something more subtle. The gravitational fields overlap, gas clouds interact, orbits change, material is compressed. A passing galaxy can awaken star formation in another system by disturbing gas that might otherwise have remained more diffuse. The cartwheel's ring is a stellar nursery produced by disturbance. Massive stars born there flood their surroundings with ultraviolet radiation. Their winds blow bubbles into nearby gas. Some will end as supernovae, scattering heavy elements and driving shocks into the ring. The ring is therefore both evidence and consequence. It marks where the encounter sent pressure through the disk, and it shines because that pressure helped new stars form. Galaxy interactions are complex because gravity acts on every part at once. The intruder had its own mass and trajectory. A slight change in angle, speed, or mass could have produced a different shape, an off-center ring, a warped disk, a stronger tail, or a less symmetrical disturbance. The cartwheel's form suggests an encounter close enough to the center to send a fairly circular wave outward, but not so orderly that all complexity disappeared. Its ring is uneven. Some regions glow more strongly than others. Star formation is clumpy. Because gas itself is clumpy, the wheel is not perfect. Its imperfections are part of the evidence, revealing that a clean concept, a circular wave, moved through a messy living galaxy. Like other bizarre galaxies, the cartwheel requires many kinds of light to understand. Visible observations reveal the blue ring and the disturbed structure. Infrared light traces dust and hidden star formation. X-rays reveal energetic sources, including compact objects such as neutron stars and black holes created after massive stars have died. In regions of intense star formation, many massive stars live short lives and leave behind such remnants. The outer ring, therefore, contains not only newborn stars, but also the early deaths of the most massive among them. Radio observations can map hydrogen gas, showing where the raw material still lies and how it moves. Together, these wavelengths turn the wheel from a striking image into a physical process, a record of gas compression, star formation, stellar death, and gravitational disturbance unfolding across the disk. There is a deeper lesson in the cartwheel's symmetry. A ring can make the universe look orderly, almost simple. But the order comes from an event that was disruptive. The shape is the visible discipline of gravity after impact. It became a wheel because a disturbance moved outward with enough coherence to organize gas into a ring. This is one of the quiet surprises of cosmic structure. Disorder can create patterns. A collision can generate symmetry. A violent gravitational passage can leave behind a form that looks balanced and almost gentle. It is peaceful in appearance because the happening was so large, so slow, and so governed by physical law that its aftermath arranged itself into beauty. Over time, the ring will change. The most massive blue stars will fade and die. Gas in the ring will be consumed, heated, or pushed away. The outward wave will weaken as it travels through material of different density. The inner regions may continue to settle, and the spokes may become less distinct. The galaxy may never return to its former spiral identity. If that identity is indeed what it once had, instead, it will carry the collision forward into a new structure, with stars formed by the impact becoming part of its later population. In this sense, the cartwheel is not an exception to galactic evolution, but a vivid example of it. Galaxies are not fixed categories moving unchanged through time. They are histories in progress. A spiral can become a ring. A ring can fade into another arrangement. The Cartwheel Galaxy stands among the most bizarre galaxies because its history is drawn so clearly into its shape. It shows the wave of an encounter still moving, the rim of compressed gas still forming stars, and the interior still bearing the marks of disruption. It turns the idea of galactic collision into something visible and readable. The ring is a sentence written by gravity across the disk. The spokes are lingering traces of rearranged matter. The young stars are the bright punctuation of a shock that has not yet finished its work. After Hoag's object, whose ring remains quiet and ambiguous, the cartwheel offers a ring with a more direct story, an impact, a ripple, and an outward moving front of creation. Yet even here, certainty is not absolute in every detail. The exact geometry of the encounter, the original appearance of the galaxy, and the future shape it will take remain part of the wider mystery. What is clear is enough. A galaxy was struck through its gravitational heart, and instead of simply dissolving, it answered with a wheel of stars, turning disturbance into one of the most haunting structures in the observable universe. The Tadpole Galaxy carries a different kind of distortion from the cartwheel. Its strangeness is not a ring expanding outward from a central impact, but a body pulled into a long, luminous tail, as though gravity has stretched the galaxy beyond its former outline. Its formal designation is UGC 10214, but the nickname has endured because the shape is so immediately recognizable. A bright spiral body forms the head, while a vast stream of stars and gas trails behind it, curving through space for hundreds of thousands of light years. The comparison to a tadpole is only visual, yet it captures something important about the galaxy's present state. It looks transitional, incomplete, as if caught between one form and another. In truth, that is what it is. The Tadpole Galaxy is a spiral system undergoing gravitational disturbance, most likely from a close encounter with a smaller companion. It has not been shattered, and it has not become a ring. Instead, its outer material has been drawn outward into a tidal tail, a structure that makes the invisible pull of gravity visible across intergalactic distances. Tidal tails form when one galaxy passes close enough to another that gravity does not pull evenly on all regions at once. The near side feels a stronger pull than the far side. Stars, gas, and dust are shifted from their old orbits and stretched into long streams. The word tide is the same word used for oceans. But here the ocean is made of stars and hydrogen clouds, and the shorelines are measured in light years. In the Tadpole Galaxy, the tail is a record of such uneven gravity. A smaller galaxy appears to have swept past the larger spiral, tugging material from the disk and leaving the bright head unsettled. The encounter did not require a direct collision of stars. As in most galactic interactions, the stars themselves were too widely spaced to strike one another. What mattered was the collective gravitational field. The smaller galaxy acted like a passing hand on a rotating disk, pulling some material outward while leaving the core still bound. The result is an elegant disruption. A spiral galaxy with one side extended into an enormous trail. The tail is not empty debris. It contains stars, star clusters, and gas that once belonged more tightly to the main galaxy. In some regions, the gas has been compressed enough to form new stars, so the tail is threaded with young blue clusters. These stars may have been born after the material was pulled outward. Inside the stretched stream itself, this is one of the recurring themes among bizarre galaxies. Disturbance can become a source of creation. A tail formed by gravitational stripping may look like a sign of loss, and it is, because the main disk has been deprived of material. But within that loss, pockets of gas can collapse and ignite. The galaxy leaves behind not a dead trail, but a thin, scattered nursery. The young clusters in the tadpole's tail may eventually drift as part of the larger system, fall back toward the main galaxy, or become dispersed into faint intergalactic light. The main body of the Tadpole Galaxy is also marked by the event. Its spiral arms are distorted. Its disk is asymmetric, and its star-forming regions are unevenly arranged. A normal spiral depends on a balance between rotation, gravity, and gas density. Spiral arms are not fixed material arms like spokes on a wheel, but patterns of compression through which stars and gas move. A close encounter can disturb those patterns, pulling one arm longer, compressing another, and driving gas toward new orbits. The tadpole's head, therefore, carries both the old identity of a spiral and the new imprint of its companion's passage. The galaxy has not forgotten what it was, but it cannot return exactly to that earlier shape. The encounter has changed the paths of its material, and those new paths will continue to evolve for immense spans of time. What appears now as a dramatic tail may later fade into a more diffuse stellar stream. Some material may fall back, raining slowly onto the disk and perhaps feeding later star formation. Some may be lost into the halo, where it will become part of a faint envelope of stars around the galaxy. Tidal tails are especially valuable because they help reconstruct the history of an interaction. Their length, curvature, brightness, and clumpiness all carry information. A long, narrow tail suggests material pulled out along certain orbital paths. A curved tail reveals the geometry of the encounter and the rotation of the disk from which it was drawn. Star clusters within the tail reveal when gas was compressed and where conditions allowed star formation. In this way, the Tadpole Galaxy becomes more than an image. It is a gravitational diagram. Its tail is the drawn path of an event, a line that helps astronomers infer where the intruder moved and how strongly it disturbed the larger disk. The smaller companion responsible for the distortion may be visible near the head, embedded in the crowded field, or already partly blended with the larger system. Its role is not measured by size alone. A small galaxy can create a large effect if it passes at the right distance and angle. The tadpole shows how delicate spiral disks can be at their edges. The central regions are held more tightly by gravity, but outer stars and gas are easier to pull away. This is why tidal tails often contain material from the outskirts of galaxies. The outer disk is the place where a passing companion can write most dramatically. It can lift material into arcs, bridges, and tails without destroying the central galaxy. There is a calm grandeur in the tail's scale. It extends so far that the main galaxy seems almost small beside its own aftermath. A structure drawn from one disk becomes larger than the disk itself, stretching through space like a record of motion, too slow to see directly. Every star in the tail follows its own orbit, yet together they form a coherent stream because they were displaced by the same event. This is one of the quiet powers of gravity. It can organize separation. It can pull material away while still preserving a trace of shared origin. The tadpole's tail is a path of departure, but it is also a sign of connection. Each star in it once belonged more closely to the main disk. Each cloud of gas carries chemical memory from the larger galaxy. The tail may look like an appendage, but it is really a dispersed piece of the galaxy's former self. The tadpole galaxy also belongs to a wider family of interacting spirals that show bridges, plume, and tidal streams. Such structures are common in the universe because galaxies often pass near one another, especially in groups where relative speeds are low enough for gravity to work over long periods. The Milky Way itself carries signs of smaller galaxies being stretched and absorbed, though the evidence is much fainter than the tadpole's bright tail. In that sense, the tadpole is not an impossible oddity. It is an ordinary gravitational process made extraordinary by timing, angle, and visibility. The universe is full of encounters, but not every encounter produces a shape so vivid. Here, the moment is clear enough to seem almost illustrative. The galaxy displays the lesson openly. A spiral can be pulled into a tail without being destroyed, and the material drawn away can continue making stars. Its bizarre appearance is therefore an exposed stage of a larger evolutionary pattern. In the far future, the tadpole may look far less dramatic. The tail's brightest young stars will age and dim. Gas may disperse, form stars, or return to the galaxy. The stream may spread until it becomes a faint halo feature, hard to detect except with deep observations. The smaller companion may merge completely, adding its stars and dark matter to the larger system. The disturbed spiral may settle into a new arrangement, perhaps still asymmetric, perhaps more regular than it is now. The striking tadpole shape is temporary, but temporary in cosmic language can still mean hundreds of millions of years. Astronomy often depends on catching these long moments. No observer watches the full transformation, but many galaxies at different stages allow the sequence to be understood. The tadpole is one frame in the slow film of galactic interaction. After the cartwheel's expanding ring, the tadpole's tail offers another way. Gravity turns collision into structure. The cartwheel shows a disturbance moving through a disk from the inside outward. The tadpole shows a disturbance pulling a disk outward into space. One becomes a ring of star formation. The other, a trail of stars and gas. Both reveal that galactic shapes are not static categories, but events extended through time. In the tadpole galaxy, the event has left a line across darkness, a long wake of material that makes the past visible. Its beauty lies in the tension between delicacy and force. The tail looks fragile, almost like a thread, but it was made by the gravity of galaxies. It marks loss, but it also contains new stars. It shows a galaxy being changed, not in an instant, but through the patient unfolding of an encounter. The tadpole reminds the procession of bizarre galaxies that some of the universe's strangest forms are not final forms at all. They are transitions. caught while matter is still answering a question gravity asked long ago. The antennae galaxies show a collision not as a single wound, but as a long transformation still unfolding. They are two spiral galaxies locked together in the slow process of merger. Their original disks pulled open by gravity. Their stars and gas stretched into great curved tails that reach outward like delicate feelers against the dark. These tails give the pair its familiar name. But the name is only the simplest description of a much deeper event. The antennae are not two solid bodies crashing in the way stones might strike. They are immense stellar systems, each once carrying its own spiral structure. Central region, gas clouds, dust lanes, star clusters, and dark matter halo. As they pass through and around one another, their individual identities begin to loosen. Their stars mostly move through empty space without direct collision, yet their orbits are changed by the shifting gravitational field. Their gas clouds, more responsive and more capable of compression, collide, shock, and collapse. The result is a galaxy pair that seems chaotic at first, but whose chaos is fertile. The merger is tearing old forms apart while building new stars in extraordinary numbers. The antennae are relatively nearby compared with the most distant galaxies, close enough for telescopes to study their star-forming regions in remarkable detail. Their light reveals a system in the middle of a major galactic interaction, a stage that the Milky Way and Andromeda may one day enter in their own far future. For the antennae, the encounter began long before the present view. The two galaxies likely approached, passed near or through each other, and then were drawn back by mutual gravity. Each passage raised tides in their disks. These tides pulled stars and gas outward into long streams, while also driving gas inward toward crowded central regions. The tails are the outward expression of the encounter. The bright knots of young stars are the inward and compressed expression. Together they reveal how a merger redistributes a galaxy in two directions at once, flinging material outward while forcing other material into dense star-forming zones. In ordinary spiral galaxies, star formation occurs in clouds distributed through arms and disks. In the antennae, the interaction has intensified that process. Gas clouds that might once have remained separated are pushed together by the changing gravitational field and by direct collisions with other clouds. When gas is compressed strongly enough, it fragments and collapses into new stars. The antennae contain many young, massive star clusters, some of them dense enough to be possible young versions of globular clusters. These clusters shine with blue light from short-lived massive stars, and they mark places where the merger has turned disturbance into birth. It is one of the most important lessons of interacting galaxies. A collision can damage familiar structure, but it can also create the conditions for sudden abundance. Spiral arms are distorted, dust lanes are twisted, and the old disks become difficult to separate. Yet within the confusion, new stars appear in bright concentrations. The gas between the two galaxies is especially active. This overlap region, where material from both systems has been forced together, contains intense star formation, hidden partly by dust. Visible light shows some of the young clusters, but infrared observations reveal more, because dust absorbs shorter wavelengths and re-radiates energy at longer wavelengths. In this sense, the antennae are a layered object. A visible image shows tails, bright knots, and distorted shapes. Infrared light shows warm dust and hidden stellar nurseries. X-ray observations reveal hot gas and compact remnants, including neutron stars and black holes left behind by massive stars that have already ended their brief lives. Radio observations trace colder gas, the raw material that may form future stars. Each kind of light shows a different consequence of the merger. Together, they reveal a system where stellar birth and stellar death are already intertwined. The youngest massive stars live so quickly that some explode while the larger merger is still in progress, enriching the gas and stirring it again. The antennae also demonstrate that galactic mergers are not brief events. The process takes hundreds of millions of years. What appears in one image is only a stage in a long gravitational dance. The two galaxies have not yet settled into a single final body, but they are already losing their separateness. Their dark matter halos overlap. Their stars are being redistributed into new orbits. Their gas is being consumed by star formation, expelled by stellar feedback, or driven inward by gravity. Over time, the two nuclei may spiral closer together and eventually merge. The final remnant may resemble an elliptical galaxy more than a spiral, with stars moving on more random orbits and with much of the original disk structure erased. The graceful arms that once marked each system may survive only as faint memories in the outer halo, while the star clusters formed during the merger remain as lasting evidence of the collision. This future gives the antennae a special role in understanding galactic evolution. Many elliptical galaxies may have formed through mergers of spirals or through repeated accretion events over cosmic time. When astronomers study a pair like the antennae, they are not only observing an oddity, they are watching a possible pathway from one galactic type to another. The universe is not divided into fixed categories from the beginning. Spirals, ellipticals, irregulars, rings, and disturbed systems are related through time. A merger can erase a disk, build a spheroid, feed a central black hole, create star clusters, and throw streams of stars into the halo. The antennae make this pathway visible because they are caught during the change, not before it or long after it. Their bizarre appearance is therefore a transitional form, a bridge between separate spirals and a future remnant. The long tidal tails are among the clearest signs of the encounter's geometry. They are made mostly of stars and gas pulled from the outer regions of the original disks, where gravity held material less tightly than near the centers. Their length and curvature help reconstruct the paths the galaxies followed. In these tails, some gas may remain cool enough to form stars, and in some cases material gathered inside tidal tails can become small self-gravitating objects known as tidal dwarf galaxies. These would not be primordial galaxies formed independently in the early universe, but secondary systems assembled from material torn out of larger galaxies. This possibility adds another layer to the merger. The destruction of two spiral disks can seed smaller structures in the debris. Gravity breaks apart and gathers, often at the same time. The antennae are filled with this double motion. Their tails carry material away. Their centers draw material inward. Their overlap region forms clusters. Their future remnant is being assembled from everything that the encounter rearranges. There is an unusual calm in viewing such a violent history from a cosmic distance. The antennae look almost like a slow underwater form, their tails arcing gently away from the bright central chaos. But the physical conditions inside them are intense. Massive stars flood nearby gas with radiation. Supernovae send shock waves outward. Dust clouds hide crowded nurseries. Gas streams collide at enormous speeds. The word collision is accurate, but it must be understood at galactic scale. It is not one sudden impact. It is a long era in which gravity continuously changes the map. The galaxies are not breaking like glass. They are being remade like clouds under pressure. Except the clouds contain billions of stars, and the pressure is gravity acting across tens of thousands of light years. The antennae also offer a comparison with the previous bizarre galaxies in the procession. M86 carried signs of older consumption and stripping inside a cluster. ESO 137001 lost gas to an unseen medium. The baby boom galaxy showed star formation pushed to an early cosmic extreme. The sombrero and black eye galaxies preserved evidence of layered histories inside graceful forms. Hoag's object and the cartwheel showed rings shaped by uncertain or collisional origins. The tadpole showed a spiral pulled into a long tail. The antennae gather many of these themes at once. They have tails, starbursts, dust, hidden gas, altered rotation, and the early stages of a future transformation. They are not a single curiosity. but a concentrated example of galactic evolution in motion. In the end, the antennae are bizarre because they reveal creation and ruin as inseparable parts of the same process. The two original spirals are losing their old boundaries. Their arms are distorted. Their gas is being rearranged. Their future will not preserve them exactly as they were. Yet the merger has also filled them with young clusters and new light. In the crowded overlap of their bodies, stars are forming from compressed clouds in their tails. Material once held in orderly disks has become an extended signature of encounter. The galaxies are changing identity without leaving the laws of physics behind. Gravity pulls, gas responds, stars ignite, and time carries the system toward a new shape. The antennae remind the cosmic story that bizarre galaxies are not merely strange objects placed beside normal ones. They are moments of transformation. And sometimes the most dramatic forms are the places where the universe is quietly building its next arrangement from the ruins of the last. The meaning of a bizarre galaxy is not that the universe has made an error. It is that the usual rules have become visible under unusual pressure. A calm spiral, seen from far away, can seem almost timeless, as though its arms have always turned in the same slow pattern. A smooth elliptical can seem finished, as though its history has settled into a single glow. But the galaxies that appear strange interrupt that comfort. They show motion, hunger, stripping, collision, and renewal in forms too large to ignore. M86 carries the signs of a galaxy moving against the local expectation of retreat, falling through the Virgo cluster while holding the remains of smaller systems in its halo. ESO 137001 shows that the space between galaxies in a cluster is not empty in any simple way, because thin hot gas can remove a spiral's future fuel and draw star-forming tails behind it. The baby boom galaxy reveals that the young universe was not merely quiet and unfinished, but capable of immense bursts of creation. The sombrero and the black eye show that a galaxy can look orderly while preserving a complicated past in dust. Hidden structure, central, mass, and reversed motion. Hoag's object shows how symmetry can be more mysterious than chaos. The cartwheel, the tadpole, and the antennae show collision becoming pattern. Tail and nursery. Together, they form a quiet argument that the bizarre is not outside cosmic law. It is where cosmic law leaves its clearest handwriting. Gravity is the first author of that handwriting. It gathers matter into halos, pulls galaxies into groups and clusters, bends disks, rays, tide, and changes the paths of stars without needing them to collide. It is gentle only in the sense that it acts continuously and at a distance. Given enough time, its effects become enormous. A small companion passing near a spiral can draw out a tail longer than the original disk. Two spirals meeting over hundreds of millions of years can turn their arms into streams and their gas into clusters of newborn stars. A galaxy plunging through a cluster can be redirected by the cluster's mass while also being stripped by the gas inside it. Gravity does not merely hold galaxies together. It also rearranges them, tests them, and sometimes takes them apart. The shapes that result are not decorative accidents. They are maps of gravitational history. A tail points back to an encounter. A ring preserves the passage of a wave. A warped or counter-rotating disk suggests material acquired from another origin. A halo rich in streams and clusters hints at older acts of absorption. In these strange forms, gravity becomes visible not as an equation, but as memory. Gas writes the second part of the story. Stars are bright and enduring, but gas is more responsive. It can collide, compress, cool, heat, and flow. It can be stripped from a galaxy by pressure or driven inward by a merger. It can form a ring when a wave passes through it, or ignite in a tail after tidal forces pull it outward. Because stars are born from gas. The fate of gas is the fate of a galaxy's future light. A galaxy may keep most of its old stars and still lose the possibility of youth. That is why the jellyfish-like galaxies are so important. They show star formation being removed from the main body and relocated into a wake. They reveal that a galaxy can be quenched not by losing what already shines, but by losing what has not yet become luminous. In the antennae, gas gathered by collision becomes a burst of clusters. In the cartwheel, gas compressed by an outward moving disturbance becomes a ring of blue stars. In the baby boom galaxy, early gas turns into stars at a rate that makes the system a furnace of beginnings. Gas is fragile compared with stars, yet it controls whether a galaxy remains active, fathes, or briefly blazes. Dark matter forms the unseen ground beneath these visible transformations. It does not glow in the ring of Hoag's object, trail behind the tadpole in blue clusters, or darken the sombrero's dust lane. Yet without its gravity, the motions of galaxies would not make sense. Stars orbit too quickly to be held by the visible matter alone. Clusters bind galaxies inside enormous gravitational basins. Extended halos guide streams, stabilize disks, and influence how debris settles after a merger. In bizarre galaxies, dark matter is not a separate mystery placed beside the visible one. It is part of the same structure. The path of a tidal tail, the coherence of a ring, and the survival of a disk after disturbance all carry clues about mass that cannot be seen directly. These galaxies are useful because they separate kinds of matter. Gas can be pushed by pressure. Stars mostly follow gravity. Dark matter remains indifferent to ordinary gas resistance and reveals itself through the motion of everything else. A stripped galaxy crossing a cluster becomes a demonstration of this difference. Its visible gas may lag behind, while its stars and invisible halo continue along the path set by gravity. Time is the quiet dimension that makes all of this possible. A bizarre galaxy is often a brief phase only in comparison with the age of the universe, but that brief phase may last longer than complex life has existed on Earth. Human language struggles here, because words such as sudden, recent, and temporary do not carry their ordinary meaning. The cartwheel's ring is temporary, but it may remain visible across hundreds of millions of years. The antennae are merging now, but there now is a long era of repeated passages, gas compression, and orbital decay. The tadpole's tail may eventually fade into a dim stream, but for ages it remains a bright signature of encounter. Even the baby boom galaxy is seen as a preserved ancient moment, its light carrying a view from a time when the cosmos itself was young. Astronomy turns distance into history. A galaxy nearby is seen in a relatively recent chapter. A galaxy billions of light-years away is seen as it was when the universe was much younger. The bizarre objects, therefore, do not all belong to one cosmic moment. They are pages from different chapters, laid across the sky at once. What they reveal is evolution, not a ladder from primitive to advanced, but a branching set of pathways. A galaxy may grow by accreting smaller systems. It may fade after losing gas. It may flare into starburst after a merger. It may settle into a smooth elliptical remnant after spirals collide. It may form a ring from an impact or acquire a counter-rotating disk from captured material. These are not exceptions to the life of galaxies. They are part of that life. The ordinary and the bizarre are connected by process. A normal spiral may contain the seeds of future distortion. A peculiar merger may later relax into something smooth and familiar. A graceful elliptical may hide the remains of many swallowed dwarfs. A ring, a tail, a black dust lane, or a reversed flow may be temporary, but the stars formed during those phases become permanent additions to the galaxy's later population. In this way, bizarre galaxies remind science to look beyond appearances. Shape is evidence, but not the whole truth. Color reveals age and star formation. Motion reveals hidden structure. Gas reveals future possibility. Dust reveals both concealment and enrichment. Black holes reveal the deep central concentration of mass. Dark matter reveals itself indirectly through all of these motions. The more unusual a galaxy looks, the more carefully its features must be separated into causes. Some strangeness comes from environment, some from impact, some from internal dynamics, some from ancient assembly, and some from processes still unresolved. The mystery is not weakened by explanation. It becomes richer, because each explanation opens another scale of inquiry. A ring asks about the intruder that made it, the gas that formed stars, the dark halo that held it, and the time over which it will fade. A tale asks about the encounter that drew it out, the stars born within it, and whether its material will return or drift away. A counter-rotating disk asks about the vanished companion whose motion still survives. The universe is not made more ordinary by understanding these things. It becomes more intricate. The most bizarre galaxies scientists have found are therefore not a sideshow to the main story of astronomy. They are among the clearest teachers of the main story. They show that cosmic structure is not static. Galaxies are assembled, altered, stripped, fed, and remade. They preserve evidence in light that has crossed enormous distances and in motions that can be measured long after the events that caused them. Their beauty is inseparable from their usefulness. The dark eye of M64, the brim of the sombrero, the ring of Hoag's object, the wheel of the cartwheel, the tail of the tadpole, and the intertwined bodies of the antennae are all forms of evidence. Each one shows matter responding to gravity, pressure, time, and environment. In the end, the bizarre galaxies do not stand apart from the cosmos. They reveal the cosmos more openly. They are the places where deep time has left a visible shape, where invisible mass has guided luminous matter, where loss has become birth, and where the slow universe has briefly arranged itself into forms strange enough to be remembered. Beyond these strange galaxies, the universe remains quiet, wide, and unfinished. Every ring, tail, dust lane, and luminous wake belongs to a larger movement that no single image can hold completely. M86 keeps falling through Virgo with old stars and stolen clusters in its halo. ESO 137001 continues to lose its gas into a cluster C. The baby boom galaxy remains preserved in ancient light, still showing a young cosmos crowded with creation. The sombrero keeps its dark ring around a hidden complexity. The black eye turns with two memories of motion. Hoag's object holds its blue ring apart from its yellow core, calm and unresolved. The cartwheel carries the expanding echo of impact. The tadpole trails its stretched material through deep space. The antennae continue their merger, turning the end of two spirals into the beginning of another form. None of them is truly frozen. Even when seen as still, each is only a passing arrangement in a universe where matter gathers, separates, cools, burns, and returns to darkness. Their strangeness does not make them less natural. It makes nature more visible. In their unusual shapes, the hidden forces of gravity, pressure, time, and dark matter become readable for a little while, written in starlight across distances too large to feel. And as their light continues onward, the galaxies themselves continue changing, slowly, silently, beyond the reach of the image that first made them known. The cosmos does not need to hurry. It has always shaped its wonders through patience, letting collisions soften into rings, loss brighten into new stars, and ancient disturbances fade into graceful forms. What remains is the quiet lesson of deep space. Even the bizarre belongs to order, and even the most unusual light is part of the same vast, gentle unfolding.